Okay, now let's get to the part where Yannet makes all of her money. Okay, so what do we mean by training? So first, let me remind you, what does it mean to make a prediction? Well, we're taking a feature vector and we're running it through the network. So what that means is if let's say the input is a one vector and our model consists of this W and this B, I get one prediction. If here's a different model, but I'm running this, if I run the same X in, I'm going to get different Y hats out of here. So prediction just means send in the input, make the computation based upon the parameters that exist in the model, and give me a prediction. Okay, that's what making a prediction means. It just means make the Y hat computation. Okay, so training is a matter of finding the optimal one of these 3 and 2 or 0.5 and 10, so that for all of the X and Y combinations in my training set, I get the lowest cost, the lowest loss. That's my goal. I want to pick 3 and 2 or 0.5 and 10. I mean, who knows what the real number is, but it'll depend on my training data and how the X and the Y's match up. What is that relationship? So you can think of it as just trying all possible combinations of the 3 and 2, whatever this W and the B are. But of course, as I mentioned earlier, that is extremely inefficient.
Terence, I don't know if you said this already, but a way to think about the loss function is some kind of error function or some kind of penalty for how bad your current model is with respect to your actual target, your Y, you know?
Yep.
It's a measure of that, basically. And we will get later. I mean, these issues are complicated. What these functions are doing, these loss functions, I think is a little bit complicated. But the way to think about it is always think about the regression loss function, like the
MSE or whatever.
The MSE or square, square R MSE or whatever. So that's your error. You're trying to the square of the residuals. That's basically what you're trying to optimize, right?
Yep.
So it's always a measure of, how bad or how good is your model, basically.
Yep.
With respect to the training data. Yeah.
Exactly. So it's a function of what you're predicting and what it should be. And typically, it's a smooth function and it tells you a lot. It can tell you more than just how close it is to the answer, particularly for classification. Anyway, so this space here is very simple. It's just two parameters, W and B, but it could be millions of parameters, could be billions of parameters. So it is quite challenging finding parameters that give you the lowest error, the lowest cost, or lowest loss. Those are all synonyms. Okay, so for regression, as Yannet said, we typically use mean squared error. We like having a smooth derivative, but it could actually be, I've seen mean absolute error. It's a little weird because the derivative is a V, which means it has a non-linearity at the 0, but apparently we're able to deal with that. Classification is a lot more complicated, at least thinking about the loss function. It's typically thought of as log loss, sometimes called cross entropy. But the idea is actually very simple. If you're very confident in a wrong answer, we penalize you. We hit you really hard with a big error, okay? So if you get the wrong answer, but you're not sure, you're kind of like 50-50, we don't penalize you very much. But if you're really, really sure that it's a cat, not a dog, but you're wrong, then you get hit really hard, okay? So that's the idea of log loss. And it's a function not of the actual target Y and the predicted class. It's a function of the predicted class, the actual class, say 0 or 1, let's think of it that way for now, and the probabilities. So it's the probability that we think it's a cat, not just that it's a cat, right? Because if we know it's a cat is true and we're predicting cat, well, we can look to see that they're the same, but we don't get like a numeric difference between these things, right? So that's why we use this log loss thing. And you'll see briefly, 0 log loss is perfect. That means there's no difference between your predicted and what it should be. And imperfection can go, basically infinitely high. In PyTorch, you'll see that there's a function called cross entropy, which is another name for this. And you're going to pass in the output of your softmax, which is your probabilities. Like I said here, you're going to pass in the probabilities that you estimate, you predict, and the known truth. Now, when you want to make a prediction, You don't have to worry about that. Once the model is trained, this is for training, and now when we're going to use it, you want to know, okay, well, what is the actual prediction? Is it a cat or a dog or what? There you just say, okay, which one of these has the maximum probability? Okay, so this is how you use it, and here's how we're training it.
Quick question.
Yeah.
Sorry.
Oh, yeah, sorry. Oh, actually, yeah. So are these the only measures of loss we use, or are there?
These are the most common. Yannet, what are there other common ones?
So we can get into different problems. So, for example, people talk about segmentation, so we will talk about other things later. Terence already mentioned, for example, for regression, we can use the absolute value. So there is also like SVM has a slightly different loss function as well for binary classification. So there are many other loss functions, and we will get into that. Terence maybe less, but I will get into a lot of different things when we talk about, for example, gradient boosting and how we can generalize gradient boosting to basically any loss function.
Another question?
Yeah, what does this sentence mean? Imperfection gives unbounded score. So
yeah, the unbounded loss, they should call that loss. Basically, the next slide will explain that.
Okay.
So I don't want to go into too much detail. We'll look at this in more detail in the machine learning class, but I just want to show you what we want. And then it turns out that the negative log loss actually gives that to us. Okay, so what we want, so remember, P is the probability that, what's the probability that class equals 1? Okay, so we want the loss function to be whatever this penalty is. Imagine we have a penalty function. We don't know what it is yet. If the truth is 1, we want it to be the penalty for our probability. If the truth is class 0, we want it to be the penalty of 1 minus P. So if we think it's 0.98, cat, if that's 1, and it is in fact a cat, then we want this probability to be low and so on. But if it's worse, if we get the wrong answer, then we want that to be 1 minus 0.98, and it had to be very penalty value at some low value. And it turns out that if you use a penalty of minus log of whatever that probability is, you get this. So here's log. We know what that looks like. Now the negative, of course, is just this. Now think about it. If we know that the probability is, we know that it's truly a 1, and we predict it's a 1 with high probability, we want this loss to be really low. But if it's truly a class 1, but we predict with, we're not really sure, we'll give it a small penalty. If we predict, because it's less than 0.5, that it's not class 1, but in fact it is, the more confident that we're not that class, the higher this value can go as we get closer to 0 here, okay? So we'll look at this in more detail in the machine learning class, but this minus log, you'll hear negative log loss, that's all this is here, is this function is negative log. And so if we use it properly, we can use it to penalize our model for being very confident in the wrong answer. And there's just a tiny bit of algebra that makes that happen. But that's all we're saying. It's not just, did you get the right answer? Is how confident were you in that right answer or confident in the wrong answer? Okay. And so multiplying by y of I and 1 minus I does nothing but gate these in and out. Okay. So this is, if this is yi is 0, then this goes away. And this one stays in. If yi is 1, then this stays in. And this goes away. Okay, so this is just getting rid of a switch statement, and then it implements this situation here. Okay, so we are simply saying if you're very confident in your answer but you're wrong, you get hit really hard, and that's why it's unbounded. Because as you get the wrong answer, you're going to be in this range, and this can go to, I assume that goes to infinity. It looks asymptotic, going to infinity there. Okay.
Does this, sorry, can I ask a quick question?
Yeah.
Does this only take into account the highest probability? So for example, let's say you're really confident for some reason about 2 of them and the slightly higher probability is wrong, but the one right under it is the correct one. Does it do anything to bring that into account?
Well, let's be specific about what we're talking about here. If it's more than a two-class problem, the math is much more complicated.
I guess I was saying more, for example, like with the softmax, when it's saying that it's putting more of the probability in one than another. If like
isn't it true that the math is not nearly so simple if it's k-class for negative log loss?
It's not that difficult, because basically what happened is that you have k logs, but you just care about one of them. You just care about the probability of the class that you have.
Okay, I thought I saw something in the
so you are just penalizing, basically the best way to do this is later with more examples,
I'm just
basically
let's not get into the K class.
Yeah, it's very similar. It's very similar actually. It's a generalization of this one here.
But if you are talking about multiple test cases, then we do the average of those penalties. Okay. So now let's figure out how we can actually use this loss function to train. Okay, so we know what the loss function is. It's your error function, your cost function. And since we know we might be using, let's say regression is a lot easier. Let's think about that. We know that mean squared error for one variable anyway is going to look like a quadratic here. It's just this bowl. So we could just randomly pick a bunch of values and figure out what the loss function is at that point. So we pick a bunch of random values along the baseline here, and then figure out going up here what its loss is, and then pick the beta one that had the lowest loss. Extremely inefficient. Instead, what we're going to do is we're going to use information about where we are on the surface of this loss function and decide to simply go downhill. What is downhill? It's the negative of the slope. The slope is a mathematical entity, the gradient that points upwards. So if we go in the opposite direction, we're going down. And we're going to have a thing called a learning rate, which tells me how big of a step I go down. Now, in the machine learning course, we'll do this in much more detail. You're going to have a big project on it. I talk about it using an analogy of the time that I got stuck on a mountain in Colorado where I was growing up in the dark. And my friend and I, Jimmy McCord, had to find a way to get down in the dark, and we couldn't. It was a moonless night, and we couldn't see anything. So what you do is you stick your foot out, and if you hit a wall, then you got to go this way because that's up. And if it's dangling over open space, you go, oh, that's down. All right. And if you do that in two directions, then you know how to move. So you're feeling around in the dark, saying, oh, the surface looks like this, so let's go this way. Okay. So that is the sort of analogy that tends to make sense. So we're going the opposite direction here, and opposite direction here. Oh. So once we know what this slope is, and the gradient is just the multiple dimension version of that word, we're going to choose a step rate, how big of a step we're going to take, and then we just tweak it. So whatever our parameters are, we're going to say my new parameter is the old parameter shifted towards lower loss. And if our learning rate is small enough, we're guaranteed to converge to something. Now, if the learning rate is not small enough, we might run into a situation like this. Let's say we have to pick some initial parameter. Remember, I told you we randomly initialize the parameters in our model. And these are also generated from our, actually, probably from the machine learning notebooks. But anyway, so we start with initial value, and I'm going to go downhill. The problem is that I took a really big step in this direction because I know this is downhill. I went so far, I went to the other side of the canyon. I'm going bang, bang, bang. I'm bouncing back and forth. My learning rate is too high. And I might just oscillate and never converge. So on the other hand, if it's so small that I go, eek, 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 it may take me forever to get there, right? And I might run out of Amazon GPU credits about right here. Now, on the other hand, if the learning rate is too big, it might not just jump over to here. It might actually jump over to here, and then over to here, and then over to here, and it will diverge and explode. And if you start seeing numbers in your loss that start to be this long on the screen and then this long, you know that your learning rate is too high. Okay, so I thought I would just kind of summarize the process you're going to go through to train a model. I mean, this is obviously just a simplified version of things, and I'm sure I'm leaving something out important here, but first thing we do is obviously prepare our data. This is assuming we have the data and then we've cleaned it up and that kind of stuff. But the basic procedure, once we have decent data, is normalize all those numerics, get the dummies, and impute values for anything missing. And then, as we discussed, at the very least, we need a validation set. Likely, we'd want a test set as well, but a validation set is needed so that we can evaluate the generality of our model. And that's how we're going to make a lot of our decisions. How do we choose our hyperparameters, and how do we choose our network architecture? Okay, so we've got to make a number of choices here, that including learning rate and regularization things, and what loss function we're going to use, and make sure that you're using an appropriate loss function. Like mean squared error is something we use for regression. We don't use it for classification. We also don't use log loss for regression. So that's for classification. So make sure you get that one right. Okay, let's see. The biggest thing when we're training our network is the learning rate and the number of epochs. If you're in British English, that's epochs. It's how many times we go through our data. It's the number of iterations. So then we're just going to run our training loop, and that's what we're going to spend a lot of time on in this class. And you run that training loop until your validation error starts to go up, or you get bored and you run through a number of iterations. So then you're going to do a lot of tweaking. You're going to sit in this training process and keep tweaking stuff until you get something you think is good. Okay, so what does the training loop look like? Well, here I've simply chosen MSE and the log loss or cross entropy for both the regression and the classification. So we're going to make a number of passes through the entire data set, and a model is going to be asked to take the entire training set and make some predictions for it. And then I'm going to say, hey, what's the loss? What's the difference between what I predict and my known truth? And this tells me something's not right in my head here. Anyway, sorry, I have a stray thought there. Okay, anyway, but the loss we're using is the mean squared error. And so we're doing this all at once. And we'll talk about vectorization here in a second, but this is a very efficient way to do it. We're not going to have another loop that iterates through each instance inside this training set. So once we figure out what this loss is, then we're going to update the parameters of the model in the direction that's going to make this loss lower the next time. And then we come back around and do it again, okay? So the exact same thing happens in the classification, except we're going to use a different loss function. And so in this particular case, we have a slightly different assumption. We're not sending out just a regression value. Remember, we're going to run through this either a softmax or a sigmoid, depending on how many classes we have. So that's why this loss function takes probabilities, not a classification for the prediction. Okay, and then otherwise it's exactly the same. So there's a slight difference in the model. Remember, we've got to have sigmoid or softmax on the end, and we're going to have a different loss function, but they're the same otherwise, the basic idea, okay? Now, so what happens when you start training this thing, when you look at how the loss goes downwards? Now, in an ideal world, the loss would be monotonically decreasing always. But because of some randomness and our step size, may not always be the case. But in general, what you're going to see is you make initially huge progress, and then it'll slow down a little bit. But if we have enough power in our model and we train long enough, you can get training loss often extremely low. All right, now that's not what we care about. What we really care about is how well the model does on data that did not get baked into the training process. So how does the model do on records that were not in the training set? And so that's what this validation loss looks like. And you can see it also makes quite a bit of progress at first, but as we start to get more and more accuracy on the training set, we tend to lose accuracy on the validation set. Why is that?
Overfitting.
Okay, what does that mean? Like, tell me more specifically, what's going on?
We're changing the network to, or the model to be like too accurate for the training data. So it's finding like relationships that are too specific to the training data. It's not general enough.
Exactly right. Exactly right. And so that's why this tends to get worse over time. Now, this curve can be quite different if we have regularization. I mean, there's lots of things that we can change, but this is a very common thing that you will see. Wow, look how good I'm doing on my training set. Well, okay, that actually doesn't really give us that much, right? Okay. So we need to regularize in some way to kind of bend this back down, or at least that's the hope. So I'll just give you the basic ideas, and we'll talk about this in depth in future lectures and or class. So the easiest thing, well, the simplest, if you can get it, is more data. And you can try augmentation techniques, like you can take your images and rotate them or shift them. So you can try getting more data. You can also try to simplify your model slightly. If it has less power, it can't chase all those details. Now, there's something called dropout, which is nothing more than simply killing some of the neurons occasionally and randomly. Okay, and that also prevents it from getting too good. There's something called weight decay, which we will know as L2 regularization, ridge regression in the machine learning class. And that's a way to simply constrain the model parameters so they don't get too big. The idea is that if model parameters are too big, they're not going to generalize well. And so that can be used as a tweak to our loss function, and otherwise the model stays the same. The other thing we can do is simply stop early. Hey, why don't you just stop right here? When the loss function for the validation starts to go up, well, stop, or pick the minimum. There's another thing called batch normalization. It is the equivalent of standardizing or normalizing variables at the input layer. We're simply going to do it in between the layers, just like we have a nonlinearity there. We're going to stick in normalization as well. It's a little more complicated, but that's all we're really doing is bringing these distributions back into a normal, I don't mean Gaussian, but into a distribution that shifts less. Okay, now the other thing we're going to do is something called stochastic gradient descent. We've been doing batch gradient descent. We're going to do stochastic gradient descent, which is adding randomness to the process by simply not looking at all the data in order to make a decision about what the lower loss is. Okay, so that's just for your future reference, and we'll do some of that in the labs. Okay, one note, you can come back and look at this later if you like. When I say vectorization, what I mean is instead of a for loop that adds two vectors like this, like a of I plus b of I, to get this vector addition, NumPy and Python and Torch and all these others, TensorFlow, let you do vector math. And so I'm adding two vectors by specifically saying a plus b. I don't have to say how to do it. I say do the vector math. And the important point here is that it gives an opportunity for the computer to do parallel processing. If it knows these are two vector operations, it's hard to look at this and go, that's a vector operation. It's easy to look at this because it knows that's a vector and that's a vector. And so it gives an opportunity for us to execute this in parallel, whether it's on multiple core on our laptops or on a GPU. I don't know if we need to go into detail, but I just want to point out that we don't have to loop. So the vectorization in the training loop, we don't have to go through at each pass through the data. We don't have to look at each record individually. We can do them all at once by doing matrix multiplications instead of vector multiplications, okay? So again, I'm not sure how important it is at this stage, but you're gonna see us do a lot of vector math, and this is why we're doing it. For one, we get rid of this inner loop, and the other, it gives us an opportunity for improved speed. Because remember, as I told you, if you're doing a loop in Python, get ready to go slow. Okay, so all we're gonna do at least in the initial part of this, when Yannet starts doing convolutional neural nets with you, it's going to get more complicated. But at the beginning, to build a vanilla neural network, it's quite simple. We simply have 3 building blocks that we tend to use. It's our linear unit that just takes a vector and moves it to a different vector space. And I've got 2 nonlinearities. I've got a ReLU and a sigmoid. And from that, I can stack and pipeline, and that's how I build my neural networks. For a regressor, the final layer transforms whatever the final layer input vector is to a single output, and that's a regressor. The classifier adds a sigmoid to the end of a regression layer for 2 class, or a softmax to a layer of K neurons. So training is just a matter of finding those parameters that give us the lowest error. We don't do that by randomly trying parameters. It would take forever. We use a gradient descent method, which means to look at where we are on the surface of this loss function in some high dimensional space and say which way is down, at least from here. And then we take a step based upon a learning rate. We take a step of a certain size in that direction. And that's it. Now you know everything. Questions? So that's just 10,000 foot view. Now
I have a question.
Okay, good.
How do we determine the learning rate so that it's not too big or too small?
Oh, it's horrible. What I do is I start small and then I start cranking it up. And when it diverges, I back it down. Now, that's the way we start out. And there's more sophisticated ways to do that, where we can turn on something that will cycle through multiple learning rates for us. But generally, it cycles through a range of learning rates for us. I think you have to tweak what that range is. So once again, you're still having to guess and check some values, but it actually can get you a much better function. It doesn't take long to get an intuition about this stuff, but I always start pretty low, like 0.001 or something, and then if it's too slow, I crank it up. All right, well, let's take a look at some actual code.